All right, we're gonna get started in about 2 minutes at 6:15. So hang in tight.
Yeah.
All right. Hello, everyone. Welcome to Lecture 8 of the Fundamentals Decal. This lecture, we'll be talking about scaling the blockchain. And basically what we'll be doing is going over a bunch of different scaling techniques that have been implemented or are in the process of being implemented in both the Bitcoin blockchain and the Ethereum blockchain. Keep in mind, these methods can be, just more general and can be implemented in the general case for other blockchains as well. And yeah, guys, please throw up a reaction just to make sure if you can see our screen, just so we can make sure that everyone can see it. But otherwise, we will go ahead and get started. Today, the table of contents, we'll be talking about, we'll go into the background of scalability, give you guys a little bit of context about why it's important and why we talk about it and why there's a whole lecture dedicated to it. And then we'll go into, we'll go right into the case studies of actual implementation. So Taproot, Sharding, Segregated Witness, Lightning Network, Plasma, and Optimistic Rollups. These are all scalability implementations that we'll be talking about in the lecture. I am one of your lecturers today. My name is Sayan. I am a second year computer science student. I've been a part of the education department at Blockchain at Berkeley for a couple of semesters now, like 3 or 4. And I'm also the director of fundraising for the accelerator. And I'll hand it off to Nishan.
Yo, what's up, y'all? So I'm Nishan. I'm one of the current co-presidents of Blockchain at Berkeley. I've been in BAB for around 2 years now. Worked with the accelerator a lot as well. So I kind of was there with Sayan. And yeah, I'm a CS junior as well. So let's get into it.
Yeah. And one thing, we'll be stopping a lot to ask questions. We'd love to make this as casual and as, interactive as possible. So please feel free to ask questions in the chat. Please feel free to just unmute and ask us questions even. And just, let's just make this a conversation and let's have a good hour and a half.
Yeah, straight up. Y'all can interrupt us at any time. I'm down for it. All right, so what is the scalability problem? We're talking about scalability today, which is honestly one of the most interesting, nuanced, and modern parts of blockchain development right now. And when you think about scalability and just what blockchains are supposed to be in general, blockchains offer all these sorts of services, right? Okay, these decentralized execution environments and okay, decentralized cryptocurrency. But if the world and people across the world and everyone in the world can't use it, how useful is it? So the scalability problem is making sure that a blockchain is able to offer its services to everyone in the world, regardless of how many people are on there interacting with the blockchain itself. Of course, you can see it very directly through things like if you've tried to make an Ethereum transaction anytime in the last 6 months, where the common trope is that gas prices are way too high. Hope you get the pun, but yeah, it's a very practical problem right now. It's way too expensive to work with all these blockchains right now. And scalability is how we solve that.
And just to like dive in a little bit deeper, right? So when we say providing all the services that a blockchain offers, we can take Bitcoin as an example, and we could be like, okay, we know from the past lectures, we've all learned that Bitcoin has privacy guarantees, it has security guarantees, it guarantees that you can be a pseudonymous user. And what we want to ensure that as the network grows, as more users join the network, and as more people start to adopt Bitcoin, that all of these services are still guaranteed for all users, right? So we want to make sure that all these services and guarantees are still in place, independent of how many users there are.
Absolutely. And the common metric that people use when they think about scalability is this thing called TPS, or transactions per second. And the common metaphor and example given is, say you want to go and buy a cup of coffee. And if you're working with something like Bitcoin, if more than 3 people are trying to get a cup of coffee at any time, I mean, you can kind of see what the average TPS is looking like. The load that you can manage with something like the Bitcoin blockchain is very slow. People often like to compare TPS to things like PayPal and Visa. It's unfair in certain ways, but we'll take it. And that's what we're aiming for when you go to something like TPS. And right now, this should be more than enough to visualize that we need to do a lot more when it comes to scalability for something like the Bitcoin blockchain. So that's just one sort of visualization. And just to make sure. And so now to just set a little bit of framework as well for what we're about to talk about, we're going to talk about all sorts of scalability solutions that are across different parts of the blockchain. So when we're going to discuss these 2 different sides, there's a layer 1 and the layer 2. So layer 1 is what you've been learning this entire time about the core blockchain architecture. So the Bitcoin blockchain, the Ethereum blockchain that uses consensus mechanisms like Satoshi consensus plus proof of work. And these are the exact blockchains themselves. So changes made here to improve scalability on the layer 1 are made on chain itself. We're changing the way that the blockchain works fundamentally. Then layer 2 build an entire level on top of your primary blockchain. So these create other networks or other networks is a good word for it, for frameworks or protocols on top of the existing blockchain.
Like
so
side chains as well.
Exactly, yeah. Or side chains is that one, but yeah, these kind of build on top of the core blockchain, which they rely on for security itself. So we'll hear about a couple of key features and key projects that are layer 2 scaling solutions. So a lot of these changes are not directly on the blockchain itself, but are other things that you can interact with that are still part of this entire blockchain ecosystem. So
yeah, and one thing to keep in mind is kind of the differences between L1 solutions and L2 solutions. We'll be going into solutions that are in both categories, and you'll see that with L1 solutions, it's much more restricted in what you can do, right? So when you're modifying the actual blockchain, you know, that base layer, you kind of have to stay within the realm of what that blockchain was meant to do. You don't have a lot of wiggle room when compared to L2 solutions, when literally, you know, your imagination is the limit, and whatever you can think of, as long as it, you know, carries over those same guarantees from the base layer, you can make it. And if it makes the system faster while also, you know, keeping up security, then that's great. And you'll see these in the examples that we go into later.
Yeah, exactly. And that's why L2 exists in the first place, because L1 changes are so restricted. It's so hard to make changes on these blockchains. So we'll share a couple of stories about that as well. So next, another piece of background information is the scalability triangle we're going to go over. You've run into a few trilemmas in your time in this decal so far. I think you've run into the CAP theorem going between consistency, availability, partition tolerance. And for scalability, we like to divide it up in between 3 topics. So first, you need to ensure security for your blockchain. Next, you want to make sure that your blockchain is sufficiently decentralized. And also, of course, is the scalability triangle, you need your blockchain to be scalable. So we're going to go through a bunch of scalability solutions and show how each solution makes compromises on each of these variables on the triangle.
Yeah, and like kind of the way you can kind of set up your mental model of how to use this triangle is any solution you can kind of imagine as like somewhere within the area of this triangle, right? And so some solutions might be more scalable, but they might decrease decentralization. So for an example of this would be like, okay, say you guys have learned about the hash puzzle that miners have to solve when they're propagating a block and they're adding a block to the end of the blockchain. This hash puzzle currently is set to be around 10 minutes. And so for every block that is added, you know, every block that's added, it takes around 10 minutes to add that block. And so you might be wondering, well, if you want, you know, higher throughput, if you want more transactions per second, why not just decrease the difficulty of the hash puzzle? You know, if we decreased it from 10 minutes to like 1 minute, for example, there we go. We already have like a 10 times increase in scalability. But the problem with that is that really, you know, takes away or drop like that really decreases the security of the system, right? The main way of preventing the 51% attack, which you may have heard, is that it just takes so much work and so much costs to actually perform a 51% attack, because the hash puzzle takes so much energy and funds to actually solve, especially if you're trying to beat out the rest of the entire network. If you were to decrease the complexity of the hash puzzle, then it would make the 51% attack almost trivial to just execute. And so, that's very detrimental to the security of the system. So that's just one example, a very dumb, basic example, a naive example of how, one can increase scalability by a lot, but also decrease security. So the solutions that we kind of analyze and evaluate are kind of going to aim to increase scalability while also keeping up security guarantees and decentralization guarantees.
Yeah, it's a great example. All right, we'll pause for some questions. You can either unmute and talk to us or hit it in the chat.
And also feel free to turn on your cameras. We love seeing faces instead of just talking to a boring old computer screen,
Ooh, yeah, I want to see some faces right now. What's up, Brian?
There we go.
I didn't realize my laptop cover was on.
No worries.
No worries.
All right, cool. Well, if there's no questions, we'll go ahead and get started into layer 1 scalability solutions. And so let's get some audience interaction. Let's get some engagement. What layer 1 scaling solutions have you heard of? And don't be afraid to be wrong. Let's just throw some ideas out there. Feel free to put in the chat or unmute. Either is fine.
Yeah.
But let's just try to get 2 or 3 answers in here.
Yeah, I just want to see something. Even guess the name of one of these layer 1 scaling solutions.
I kind of mentioned a couple of the table of contents, but
oh, all right. Time
see who's paying attention.
Memory exercise.
Technically, yeah, that is scalability solution. And that would be layer 1. You're correct, because the hash puzzle is kind of on the base layer that's built into the core protocol. So there we go. Proof of stake.
I wish, man. I wish that was a thing.
I guess proof of stake is a scalability solution.
Sort of.
More of a consensus mechanism.
Yeah.
It would replace proof of work, which you guys have learned about. Instead of putting in all this electricity and solving a hash puzzle, proof of stake, you're actually staking your ETH, for example, in ETH 2.0. And so you can, that's kind of a scalable solution. You don't need
in a way,
like the costs, but
yeah, proof of work. There are proof of work implementations that are faster than proof of stake implementations. I think proof of stake was mostly a kind of response to the whole
environmental
which
people are complaining about that, which is a very fair point. But yeah, good answers.
Yeah.
Let's try to get one more. Anyone? Maybe something along the lines of lightning or anyone? All right, that's fine. Hopefully after this lecture, you guys will all have a couple more answers to give us. But let's go ahead and get started. Well, the first layer 1 scaling solution that we will be talking about today is Taproot. Taproot is a Bitcoin improvement protocol. And what that means is this is kind of a proposal that a bunch of Bitcoin core developers proposed to the Bitcoin core team. And this is something they're working on currently. Taproot is one of the biggest changes to happen in recent Bitcoin history. And it's actually even right now under development. And so this is just an example of how early you all are in learning about Bitcoin, and how anyone can get involved with just these serious, significant changes that are happening to the Bitcoin network. But anyways, let's talk about Taproot. So there are some very clear kind of focal points that we can focus on when looking at where we can improve, what we can improve in the system to scale. And kind of one of the first things with Bitcoin, at least, is signature verification. Signature verification literally happens everywhere. So many signatures are verified every second. The first case that we can see signature verification, or a lot of signature verification, is when new blocks are validated, right? So when a miner is like told about a bunch of transactions, and when they want to put a bunch of these new transactions that are floating around the network into a block, the miner has to go through each transaction and verify the signature of each and every transaction before putting it into the block. Remember from earlier lectures, a signature is how you prove that your identity is you have the correct identity that is allowed to spend some transaction of the network, right? And so the naive method of proving your identity is showing everyone on the network your private key. If you show everyone on the network your private key, then everyone can see that, oh, this transaction was sent by Alice to this private key. I own this private key, therefore I am able to spend this transaction. The problem with that is if everyone on the network knows about your private key, well, then everyone on the network is able to access your funds and spend your funds, and you would get robbed of all your Bitcoin. So we don't want that. Instead of that, we have signatures, which is some cryptographic magic that really smart people came up with, so that you don't have to show your private key, but you're still able to mathematically or cryptographically prove that you are indeed the person corresponding to the Bitcoin public, the key that the transaction was sent to. And so, as I mentioned, the first case where we see a lot of signature verification is when miners are validating new blocks. And as you know, new blocks are constantly being added at all times in a Bitcoin network. The second case is when a new node connects to the network. So say I just got a Bitcoin, I really want to get involved, I want to participate in the network. I would go to the GitHub, I would download the Bitcoin Core wallet, and I would run through the installation process. And during the installation process, there's this there's these couple of steps. There's a step called IBD, or initial block download. And what happens in initial block download is I, as a new node, I download every single block since the Genesis block of the Bitcoin network, because I need to have access to it. As this is under the qualification that I'm a full node. Full nodes download the full network. And so when I download all these blocks from the past, I'm also simultaneously verifying these signatures, because as a new node, I want to make sure that I'm downloading the blockchain that is honest, downloading the blockchain that is true. And so to do that, I verify the signature at every point and make sure that I'm downloading the correct blockchain. And so as you can tell, signature verification is happening all the time, but it's very, very slow, prior to Taproot. And Taproot kind of fixes this, and we'll go into how it fixes it later on. Additionally, Taproot fixes some privacy vulnerabilities. You guys have probably heard, or you guys have learned in previous lectures about multi-signature wallets, and you guys may have kind of heard about Bitcoin scripts. Bitcoin scripts are just expressions that can be evaluated to true or false, and based on whether it's evaluated true or false, it allows the user to spend a transaction or not spend a transaction. And so, as you can, it's basically like Bitcoin's version of smart contracts. It's not as robust as Ethereum smart contracts, but still allows for some logic to be involved. And so previously to Taproot, what happened was in transactions, as you know, are publicly available to everyone on the network. And a transaction that included a bunch of Bitcoin scripts and a bunch of multi-signature wallets, these were able to be observed and analyzed by anyone in the network. Anyone could see which signatures were involved with the multi-sig wallet, or which scripts, worked on the condition of different signatures. And so all of this information was completely publicly available to everyone. And as you can tell, that kind of leads to some privacy vulnerabilities. Maybe you don't want an attacker to know, or you definitely don't want an attacker to know, under what conditions you wanted, I wanted Niche to spend a couple of Bitcoin, or Niche wanted me to spend a couple of Bitcoin. So as a network, we want to make sure that all of this information is obfuscated and is as secretly viewed as possible. And so what Taproot is, as I mentioned, the actual Bitcoin improvement protocol. It's the name of it. And what Taproot does is it integrated Schnorr signatures into Bitcoin. And so Schnorr signature it's a type of signature. It replaced ECDSA signatures, which you guys probably learned in lecture 3 or 4. These are the signatures that are used in the Bitcoin network to verify transactions. And the reason that we kind of incorporated Schnorr signatures is because, mathematically and cryptographically, Schnorr signatures are better than ECDSA signatures in literally every way. If you're into cryptography, I definitely recommend looking into Schnorr signatures and ECDSA signatures and kind of the pros and cons of both. Schnorr signatures win in almost every case. The reason that we didn't include Schnorr signatures previously, and the reason that it's only just now being added, is because the guy, or the professor, or whatever, who developed Schnorr signatures had patented it. And so we literally couldn't until recently. I think the patent was lifted or something, and it allowed Bitcoin core devs to add it. And so that's really cool. And Taproot also integrated Merkleized abstract syntax trees, or MASTs. And you guys might be familiar with the term Merkle, because we learned about Merkle trees back in earlier lectures. Back then, Merkle trees were used for transactions and making sure that the Merkle root was unchanged to make sure that the blockchain was unchanged. But now we're using them a little bit differently, but we're still using that same underlying data structure. And so one of the main ideas of Taproot is making signature validation faster. Because if we're able to make signature validation faster, then not only are nodes able to join, or not only do we decrease the barrier of entry for new nodes, because we don't have to spend as much time verifying billions of signatures, it also makes everyday use of the Bitcoin blockchain faster. It increases throughput because miners, as they're validating signatures on a second by second basis, they're able to do this faster. So this kind of just propagates throughout the rest of the network. And so the way that it's able to do this is through Schnorr signatures, because Schnorr signatures, through some cryptographic magic that I honestly don't really understand because I'm not a cryptographer, Schnorr signatures offer key aggregation and also verification in linear time. And so let's see if the next one. Yeah. What this means is the benefits that Schnorr signature brings specifically are, it allows, first of all, for multi-signatures to look the same and cost the same as a single signature. Now, this is pretty huge because more and more multi-signature wallets and multi-signature kind of transactions are becoming more and more popular. An example is if you have a Coinbase account and if you have a Coinbase wallet, well, that's a multi-signature wallet. I think it's like, I don't know if it's actually implementation, but you kind of think of it as like a 2 of 3 multi-sig wallet where you own 2 of the keys and Coinbase owns 1 of the keys. And so what this allows is for kind of like a fault tolerance. If you were ever to lose one of your keys, then Coinbase could step in and, okay, first off, if you were to lose one of your keys and it was just you by yourself and you needed 2 keys to unlock the wallet because it's a 2 of 3 wallet, then you would be screwed because you lost one of your keys. You can't unlock the wallet because it requires 2, but you only have 1. So then all your funds in that wallet will be gone. But what multi-sig allows is, Coinbase has one of the keys. So if you ever, in a scenario that you lose one of your keys, Coinbase can step in and help you unlock it. So as you can tell, multi-signature wallets just, there's so much more functionality with these wallets. And so they're becoming much, much more popular. But the idea behind Taproot is it makes verifying these multi-sig transactions, cost the same as just a single transaction, which is, greatly increases efficiency. And also, if any attacker is trying to maybe map out the network and see, which multi-sig wallets are going where and which addresses are linked to other addresses, well, they wouldn't be able to do so after Taproot because multi-sig transactions look the same as a single signature or as a single transaction. What Schnorr also brings is batch validation. And so previously, I think signatures had to be validated in kind of in a serial manner. You had to do one after the other. But now this allows for parallelization of signature validation. And if you're a computer science, parallelization just makes everything so much faster. Multi-threading and all that.
Always.
And so, with the onset of batch validation, you can tell that not only are, as I mentioned, new nodes able to join the network quicker, but also miners are able to propagate new blocks faster, which just increases the efficiency of the entire network. And also an interesting note about the Bitcoin scripts. In one single transaction, you can include many Bitcoin scripts. Say, say I'm giving Niche some money, but I want him to only use the money after 2 weeks, or only use the money after he has 0 Bitcoin left. And so whichever one of those comes first, then he'll be able to access the funds. But so before Taproot, anyone on the network would be able to look at both of those spending conditions, both of those Bitcoin scripts, and be like, okay, that's pretty interesting. Maybe Niche is like poor and he's like losing some money, and that's why Sayon is trying to give him some money when he reaches 0. Or maybe there's some other assumptions that can be made.
Yeah.
After Taproot, now only the spending conditions that's actually activated and results in true. So only the spending condition or the Bitcoin script that allows Niche to access the funds is actually publicly shown on the network. So as you can tell, this leads to some privacy benefits. Let's go to the next one. Bada bing. Okay. And so, as I mentioned, more privacy, all these different transaction types, multi-sig transaction, transaction with scripts, they just look the same as a regular transaction. So for anyone who's trying to kind of, as I mentioned, map out the network, because that's an actual thing that attackers do. They want to see, which transactions are going where, which addresses are like sending to other addresses more frequently, because all of these are potential attack vectors. Taproot just, makes everything look the same. And so attackers are very confused. They don't know. It's just reducing the amount of knowledge, information that attackers have, which is, by far one of the best ways to prevent attacks. And as I mentioned, all scripts of a transaction are not broadcast to everyone to see. In terms of functionality, because evaluating signatures is so much faster, we can now have much larger KFN multi-sig transactions. You might be wondering why this is useful. I can't really think of an example, but I'm sure, in some weird case, we want to vary, like maybe like an organization,
or stuff like DAOs, yeah,
DAOs actually. That's a perfect example. With a DAO, you have people all over the world globally, interacting with a wallet, and so maybe you have some kind of condition where if 2/3 majority or supermajority agrees on something, then you can access funds to actually use those funds. Beforehand, that would take a lot of compute power, a lot of time and energy to actually accomplish. But now with the benefits of Taproot, that's much faster. That's a huge scalability plus, and we can now use much larger scripts because not all scripts are broadcast on the network. Only that one script that's actually evaluated. Are there any questions? I kind of talk a little bit fast, so if you want me to slow down, please let me know. But if there's any questions, I'd love to answer them. Let's just have a also any conversation about anything you guys want to have. That'd be great too, as long as it relates to the lecture, of course.
Let's get it going.
I'll stop for maybe 60 seconds.
Yep. Y'all can type it out in the chat as well. Oh yeah, you wanna hit on that into our beautiful trilemma?
Yes. Okay, it's a very good question because Taproot, honestly, and these aren't really the words of me. This is the words of John Newberry. You know John Newberry. He's a Bitcoin Core dev. Super. He's done so much for Bitcoin Core. He's one of the most active Bitcoin Core devs. He leads this workshop called Bitcoin Core Optech, and that's actually where I got the stats for. Let's go back. Oh, you went back to the triangle.
Yeah.
You can see at the bottom here. That's where I got the stats for the evaluating Taproot and how much more efficient it is. So John Newberry in this workshop kind of jokingly, kind of said that like Taproot doesn't really have that many drawbacks, right? And he was kind of joking, but also it is really true. Taproot, as you can see, increases scalability just because signature validation is much faster now. It also increases security because, like I said, there's so much more privacy because all of transactions, transactions beforehand look different. You could kind of pinpoint the multi-sig transactions and the transactions with interesting scripts, and maybe you could find attack vectors for any of them. Now they all look the same, so that's better for security. And in terms of decentralization, don't really see how it affects decentralization.
Yeah.
It's just it kind of doesn't really touch it. So yeah, Taproot, like the reason that it's so ingenious and it's so like clean and just a great update is because the benefits and the pros are so huge and so monumental, and the drawbacks is they're kind of minimal. And people don't really talk about it.
Yeah, honestly, Taproot is just a general modernization of everything in Bitcoin. So
Exactly.
Overall, it's pretty great.
Exactly.
We're going to see a few more just other scalability solutions that are a little more ambitious in what they do.
Yeah, definitely.
And those
there's
will have
drawbacks.
huge trade-offs. Yeah.
But great question. Yeah.
Yeah. Good question.
Anything else? I highly recommend. I didn't go into much of the technicals because, as you can imagine, this is a super technical, BIP. But if you're into that stuff, if you're cryptographically inclined, I definitely suggest look. There's you can hit me up, hit Nisha. We have a bunch of resources on Taproot and a bunch of dialogue around Taproot and why it's so great.
Yeah, we can even point you to regular discussions that people have in the Bitcoin community about stuff like Taproot and other Bitcoin improvements, which are really fun.
Yeah. So definitely suggest checking that on your own. otherwise, we shall move forward. Let's go all the way past Taproot. And now we're going to talk about segregated witness.
The infamous.
Yep, the infamous SegWit. I have here in the header, it's kind of L1 and L2, and you'll understand why by the end of it. But yeah, let's talk about SegWit. So what problems did SegWit solve? Well, before SegWit, there was this issue called transaction malleability. And so what this means is you can kind of imagine a transaction as like the essential parts of a transaction, kind of are the inputs, how much Bitcoin is being inputted, the outputs, how much Bitcoin is being outputted, and like who's sending it to who, right? So those are kind of the essential parts of the transaction that really define what a transaction is. The thing with transaction malleability is inside of these, if you look at transaction raw data, which we will in the next slide, you can see that there's a field that wasn't essential to the transaction, but it could still be modified. A couple of characters could be changed. And why does this matter? Well, to come up with the idea of a transaction, we input the transaction as we use a transaction as an input to a hash function. And as you learn with hash functions, they have this thing called the avalanche effect, where if you change even one bit in the input, then the output is completely different. So you can imagine what we want on the network is for two transactions that do the same thing, right? That send the same amount of money from Alice to Bob to have the same ID. But what transaction malleability shows is that, when people modify this singular bit that wasn't essential to the transaction, then the transaction ID or the hash would be completely different. And so what you could have is like multiple copies of the transaction in the Bitcoin network that all did the same thing, sent the same amount of money from Alice to Bob, but had different IDs. And so this kind of, you can imagine this leads to like a network flood attack where an attacker could just span the network with a bunch of the same transaction, essentially just like split the network in that way. So that's a very roundabout definition of transaction malleability. And that was like the main problem that SegWit fixed. In addition to transaction malleability, SegWit also fixes a very inefficient script versioning system, which we'll talk about later. The script versioning system just refers to how Bitcoin scripts were updated. Bitcoin scripts is kind of like a programming language in and of itself. And so programming languages change over time, and the same thing happens with Bitcoin scripts. But the way that they change, the updating process was very inefficient and very hard to actually use. In addition to that, there were also some inefficiencies regarding signature hashing operations, and also we saw signature data everywhere. And the reason that we don't really need to see signature data everywhere is because as users of the Bitcoin blockchain, when we see that like a block is like 100 blocks deep from the end, from the very tip, we kind of assume that it's valid, it's been verified. We trust that the miner and other people in the network have successfully looked at the transaction inside that block and verified it. And so we don't really need to keep the historic signature data inside those blocks because, rather than keeping the data, we could just include more transactions. Therefore, in a way, increasing the block size of the block. And so these are, some of the main points or the main pain points that SegWit fixed. And we'll go into each of them in more depth. So I promised that we'd see the raw data of a transaction. Here it is. This is kind of a simplification of what a transaction actually looks like on the Bitcoin blockchain. So we see we have a VN field, and that's the kind of, the inputs. We have the transaction ID. This is the ID I was talking about. And we have this V out. And inside this V out field, we have a script sig field. And so what this script sig field meant is this is where we kind of hold our witness. This is where we kind of put our signature to prove that we are able to actually use this transaction. Or it's also like the witness data, like how we're able to actually use the transaction. And so this was the field right here, this field that's not essential to the transaction, right? If we think about before, the fields that are, the aspects of a transactions that are essential to it are the input, the output, and who's sending the money to who. This doesn't have anything to do with that. This is kind of just, post-mortem, like this is like how you verify the transaction. And so as you can see, if you were to modify, even one character in the script sig, then the entire transaction ID would change because we're passing this entire, this bit string into a hash function. And so if even this, like if even one character in here is different, then it would result in a completely different ID. But now afterwards, we've moved this script sig outside of this v out field. And what that means is it's pretty much outside of the transaction, or outside of the essential parts of the transactions that's actually hashed to create the identity of the transaction. And so what happens when we move it outside is, even if we were to change anything here, then we're not modifying these fields inside the actual transaction. And so we can't, and so we know that the essential parts of the transaction are what's hashed, and that won't change. So the transaction ID will stay the same, and therefore we've kind of solved the transaction malleability problem. And this is kind of, the main thing that Segwit did. It just kind of moved the witness data outside of the transaction to the outside of the, just basically to the outside of the transaction. A very simple change, but huge, consequences throughout the entire network. And you might be wondering, like, if we move the signature outside the transaction, then like, is it not found in the blockchain at all? Well, it's still there, just in a kind of different structure, right? And this is where we'll see this Merkle tree structure pop up again. In the original Merkle tree that we learned back when we were learning about what a block actually contains, we learned that Merkle trees, the nodes contain the hashes of transactions, and those hashes are kind of concatenated together to make the hashes of the upper layer. And these hashes are propagated all the way up to go up to the Merkle tree root, the Merkle root, which you can think of as a hash of all the transactions inside the block. Instead of transactions, however, we can actually replace the transactions with signatures, but also mirror the structure of the transaction Merkle tree, so the signatures kind of match one-to-one, so that you have transaction A signature, transaction B signature, and those are concatenated all the way up. And so what this allows is you're able to formally prove that a signature of a corresponding transaction is actually included in a Merkle tree through a Merkle proof. And that's how we can kind of keep the validation properties a part of the blockchain. With script versioning and signature hashing, these were more minor changes, I would say, but also very important. So with Bitcoin scripts, the way that Bitcoin scripts were updated previously was that the opcodes that make up a Bitcoin script, there's about, 10 to 20 opcodes. And the way you would update Bitcoin scripts before Segwit is you would have to take an opcode, delete it, and then override it with a new opcode that would, perform the functionality that you wanted. As you can tell, this is kind of a jank way of updating scripts. Maybe you want to like keep all the opcodes and just add a new one, or maybe you never know down the line when you'll need an opcode. So this is kind of not the most ideal way of implementing updates. What Segwit actually allows now is an introduced version numbers, so that upgrading to a new script version could be done simply by increasing this version number. There's some details abstracted away, but basically Segwit just simplified updating scripts. And what's cool about this is Segwit is actually already implemented in the Bitcoin network. It's completely integrated, and it was integrated much before Taproot. And Taproot actually takes advantage of this update to script versioning. And so when Bitcoin core devs said they wanted to add Schnorr signatures to Bitcoin, they could just use this script versioning number, this script versioning system, and just kind of like change the number to a version that they actually wanted to incorporate Schnorr signatures into transactions, which is really cool. So we already see the benefits of Segwit happening today in terms of scalability. And for signature hashing, this is kind of much more technical stuff, but basically what happens is it resolved the issue of quadratic time signature hashing. So when you double the number of transactions, you double the number of signatures, but that would result in like quadrupling the number of quadrupling the cost of actually validating those signatures, because data is actually quadrupled. But now it only verifies each byte. It only hashes each byte at most twice. So instead of quadratic time, it's 2n time. And so we go into the pros and cons of Segwit, and we can see that the pros is that it fixes transaction malleability. Remember, we move the witness data outside of the transaction, And so transactionality is fixed. And the reason this is so huge is because this actually paves the path for Lightning Network to come into play. And Lightning Network is an L2 solution that we'll talk about later on. And you'll see why this is so huge, because Lightning Network can really change the face of Bitcoin. Additionally, Segwit was a soft fork, and so it didn't require the entire network to fork, which would be a hard fork. Bitcoin core devs really do not like hard forks because it divides the network, and we want the network to be as unified and as big as possible for decentralization purposes. It increased efficiency, as you can tell, through the sig hash operations and also the script versioning. It did increase block size. Part of the Segwit update was to increase the block size by a couple of kilobytes, or maybe like 1 or 2 megabytes. Not too much, but it was still
very minor.
Yeah, very minor block size increase, but still you can fit more transactions in there, so that's a scalability increase, and also resulted in a smaller size of blockchain because you don't have that historic signature data found everywhere. In terms of cons, like we said, it was just a one-time linear capacity increase for block sizes. So like it's cool for a little bit, but you know, we'll need more scalability solutions in the future. There's also obligated all wallets to upgrade. So all nodes had to take the responsibility to update their software, their wallet software, to be compatible with Segwit. And even though Segwit is backwards compatible with transactions that are pre-Segwit, nodes are still incentivized to use Segwit because it has a lot of has all these benefits. Also, better ways to solve transaction malleability exist. This isn't the most optimal or ideal solution by any means, but Bitcoin core devs, they kind of have to keep into account the wants and needs of all three users or all three parties of the Bitcoin blockchain. So developers and miners and just regular users, they have different needs and they have different, pain points. And so this was kind of a compromise, or the best compromise they could come up with to solve transaction malleability. Are there any questions about Segwits?
Let's see them. Yeah, once again for the trilemma in Segwit, it's kind of similarly just a general increase in benefit for all three. Nothing too crazy there.
I guess, let's see. Scalability definitely increased. Security, security increase. The network flood that's prevented.
Yeah. Also, just the enabling of things like the Lightning Network, pretty great for scalability.
Decentralization. Again, decentralization seems almost untouched.
Pretty tangential.
Yeah. Basically, the things that affect decentralization are like, if you have like, well, you'll see when we talk about like a network. There'll be some really good examples. But any question about Segwit? Segwit also is really cool to study. There's a lot of very nuanced things. So much discussion went into it. Also, like there's a whole series of Bitcoin drama that went into Segwit. Miners hated Segwit because there's this thing called ASIC boost that it's kind of like it just makes mining much more efficient, or like
slightly easier. So
slightly easier, and like you kind of have an edge on like people who don't use ASIC boost. You have an advantage with ASIC boost, and so obviously as many miners, the miners wanted to keep that advantage, but Segwit broke ASIC boost, and so there's a whole like standoff between the miners and the Bitcoin core devs. The miners being like, no, we're not going to update, and the Bitcoin core devs being like, no, you have to update. With the devs, like you gotta accept this change, and it improves the Bitcoin blockchain. And there's a whole back and forth. There's a whole drama. Really cool to see this this dialogue between miners and devs. Highly recommend looking into that. And also we have like resources on that.
I think the article Long Road to Segwit.
Long Road to Segwit. It really was a long road.
So it's an emotional
journey. One of the most emotional Bitcoin improvement protocols, I would say.
But any questions for us? We're here from.
I've been talking for an hour.
I know, man.
Time flies when you're having fun.
Time flies when you're talking about blockchain. All right.
Seems like we're good. Let's go into sharding.
All right. Now we're going to talk about another L1 blockchain improvement, which is sharding. This is getting into just completely revolutionizing the way that a blockchain is designed and looks, essentially. So sharding should kind of harken back to other mechanisms in computer science, such as database sharding. So we have a little diagram here showing how oftentimes if you have a huge ass database and you're trying to make queries to it, if the entire database is here having to manage every single query for every single piece of data in the entire database, it can get a little overloaded. But the improvement that you can often make for things like databases is sharding a database. So splitting up so that it's here for half of the user IDs, you go to one specific subset of the database, which has its own query response system. Or if it's greater than 500, the other half, you go to the other shard of the database. And it's very, very similar for blockchains as well in blockchain sharding. So now you have your blockchain state, right? The entire history of the blockchain, every single block. In a normal blockchain, every single block is to be managed, and every miner is responsible for every single block in something like a traditional blockchain. But in a sharded blockchain, a blockchain is instead split into a bunch of sub-blockchains that together will make up the entire blockchain state. So each sub-blockchain will have its own set of full nodes, i.e. miners, that will manage the consensus and block production and propagation for that singular blockchain. So in that case, you're almost creating this like multiplicative effect of, okay, now we have a 10, 20, 30, basically the number of shards you have times improvement in the scalability of your blockchain. So that in theory is amazing. And that's why many blockchains have kind of turned to sharding as the go-to scalability solution on the L1 side. So you might hear about the Near blockchain, and they, from the get-go, started as a sharded blockchain. We're also going to talk about Ethereum 2.0 a little bit at the end, and ETH 2.0 is all about moving to a sharded blockchain. I think they're going to have maybe 32, 64 shards for Ethereum itself. So just imagine the multiplicative effect of scaling for something like that. There are a lot of things to keep track of when it comes to sharding. You're going to have a bunch of different types of nodes. You might have nodes that are simply responsible for one shard. You might have systems where nodes will hop and nodes/validators will hop around different shards, like Near, which is a pretty interesting concept. You might have other nodes that manage different shards themselves, or super full nodes which manage the entire blockchain still. And when it comes to sharding itself, a couple of challenges, I'll list a few of them. So the biggest one when it comes to sharded blockchains is, okay, if you have these 64 different parts of your blockchain, say one transaction needs to make it from one side to the other, one part of state to the other, and you need to make a transaction from A to B, from one shard to the other. To be able to maintain that and make that transaction happen is a huge distributed systems problem in itself. It calls upon the concept of data availability, which is this whole other concept when it comes to blockchains about, okay, am I able to query the state of a shard properly? Am I getting the proper live version of the state of this shard if I'm coming in asking from another shard? So it's very, very interesting. A lot of communication needs to happen there. And that's where sorts of attacks like single shard takeovers can come over, where now in things like sharded blockchains, there are other attack vectors where, okay, now we don't have to worry about taking over the entire blockchain. What if we think about just taking over a singular shard, which is a fraction, sometimes 1% of the blockchain? And say you do that, say you take over a single shard of this blockchain. If a bunch of these other shards are trying to communicate with you, you can cut off communication with them, you can lie to them, you can do all sorts of things to just disrupt the blockchain itself. And if you're not implementing things like cross-shard communication and kind of just behavior and incentive alignment properly, single shard takeovers can absolutely just freeze a blockchain. It's happened in the past and it's been pretty crazy. So a lot of considerations when it comes to sharded blockchains, but the promise of scaling is huge. So that, if we go back to our little triangle, I won't scroll all the way there, is a great example. Sharding is a great example of how balancing things on this triangle. Oftentimes with sharding, you are increasing scalability significantly, but then when you go to something like decentralization, you get a little more worried because, okay, now you split the blockchain so small that there are now these smaller pieces that you might be able to take over and still have a impact on the blockchain that you wouldn't have had if it was just one big old blockchain. Security guarantees are generally the same when it comes to sharded blockchains, as long as you're implementing it properly. Otherwise, there's no reason you would want to go to sharding, honestly. So it's just a little more difficult in security, but you're still maintaining those guarantees. But that is sharding. So we'll pause for some questions about sharding in general. It goes very, very deep, and I actually did a little deep dive on sharding on Blockchain at Berkeley's YouTube, and that was a whole hour-and-a-half conversation in itself. So if you want to go into sharding in general, I think I did the near Nightshade model. You can just deep dive and watch that one, because sharding is a whole nother topic in itself.
Yeah, I mean, honestly, all of these are like, all of these could be our lecture in and of themselves, and we're just giving you a little taste of each of them. But
seriously,
any question?
But yeah. There it goes.
We get a little thumbs up from people who are still awake.
Is all this kind of making sense? Catching up in our hands.
1 thumbs up, 1 check mark, 2 thumbs up. We like that.
Thank y'all. Yeah, scalability can be pretty complex, honestly.
Yeah.
But honestly, from this lecture, we just want to get the general intuition of thinking about, okay, I'm messing with this sort of a blockchain. Okay, a blockchain can be split up, or okay, we change the way that we're doing consensus, or you can just change the way it's structured into the signatures and stuff.
Exactly.
That's all we really want.
Yeah, if you're able to leave this lecture with, okay, here are a couple of the popular scalability solutions, and also here's how I can think about these scalability solutions, and also evaluate any other solutions that I come across, in my own reading, then this lecture will have been a success. So yeah, definitely ask us questions about that, just to make sure you guys, so we can hit it home. But without further ado, we'll go ahead and go into layer 2. I'm going to ask the same question. What layer 2 scaling solutions have you heard of?
Let's hear it.
These are the big boys. These are the
these
game
are
changers.
These are the popular kids at school right now.
The kids who pull with Porsches.
All right, let's hear one of them.
Let's get 1 or 2.
One of them is named after a weather phenomenon.
Yes, thunder and come on. There we go.
Oh,
right in a word, big brain. How about another one? I mean, Ethereum has a lightning counterpart. You can mention that, or
the fourth state of matter.
Yeah.
That's interesting. I actually wanted to talk about this a little bit in this lecture, because when it comes to things like Bitcoin, we see, okay, these numbers of 3 TPS, but then when you go to something like Coinbase, and also thank you, Plasma, when you go to something like Coinbase or Binance or any other sort of centralized system where you're transacting with Bitcoin, you're like, this is pretty quick. This is happening very quick. Bitcoin doesn't seem small to me. And that's honestly because these centralized platforms are making huge trade-offs on these things like decentralization. When you do transactions on these kind of centralized apps and exchanges, oftentimes you're not directly working with the blockchain itself. You're just working with their servers and their databases, and you're just changing entries there. And then they will, in the end, transact with the blockchain on their own time, because they can do that as a centralized authority. So it's kind of a haphazard way to do it, and that's how it was at the beginning. And it was very weird to people, because you're kind of like, okay, I'm working with a decentralized cryptocurrency, but then now as I'm transacting with it, okay, I'm fast because, okay, I'm doing this non-decentralized, but there's a way to be decentralized and fast, and that's what a lot of these scalability solutions are for. So something like Coinbase sort of counts. It is what makes and has made blockchain transactions possible for people around the world to use. That's why Coinbase has millions, I think around 1 million users.
IPOing soon too.
Exactly. That's why they're worth 100 million.
100 million.
Yeah.
Something like that. Some crazy number.
Yeah. Maybe billion. I might be in the wrong scale, but yeah, they're sort of touching on what scalability is about, but these are almost on the protocol level of, okay, let's change the way these blockchains actually work. So that you don't need like centralized authorities to start controlling like where your Bitcoin is coming from and how much, like how you get your Bitcoin, basically.
Yeah, but your analysis is absolutely correct, Ryder. It definitely
Yeah.
does decrease decentralization so much, and also, but it does increase scalability, right?
It does, yeah.
More people are able to access it, which is better for the network. So yeah, trade-offs are definitely included. But yeah, great answers all in all. Let's move forward to the Lightning Network. Lightning Network is super complex. There's a white paper that is what, 14 plus.
Try like 40. Yeah,
yeah,
like
some
that, yeah.
crazy number of pages long.
Yeah.
Definitely look into it. It'll take you a while to get it. I haven't completely gotten it myself, but Lightning Network is super cool. And so let's recall for a second that this might seem very elementary and this might seem very obvious, but every transaction is put onto the blockchain. This is what we've been taught from day one. That's how we're able to guarantee that transactions are fully able to be settled by the system. That's how we're able to know that our Bitcoin has been successfully transferred from me to Niche, or Niche to me. And the classic example of kind of using blockchain or using Bitcoin that Niche already mentioned is buying a cup of coffee, right? And so say you pull up to your local Starbucks and you want your frappuccino and you want to pay in Bitcoin. Well, best practices dictate that when you pay with Bitcoin, you want to wait for about 6 blocks after your block to guarantee that your transaction has been put onto the honest and correct blockchain, and to guarantee that it's able to be settled, right? It's able to guaranteed that your transaction, your Bitcoin has gone through. And so recall that 1 block being added is about 10 minutes, so 6 block confirmation time corresponds to about an hour wait time, which just means that by the time you've confirmed that your block has gone through, that's basically like your coffee is already cold and you don't really want to eat it, and you've wasted an hour of your day. And so additionally, each transaction has a transaction fee. This transaction fee is kind of what goes to the miners. It's kind of what incentivizes them to choose your transaction out of the thousands and millions of other transactions and actually put it into a block. These fees are very inconsistent. They vary with regards to the volume of transactions in the network, or maybe a price spike or news even. It's just very inconsistent, and they could spike or drop without any warning. It's also very not economical for low value items, right? So say the fee is like 10 cents in USD when you convert it, and you're paying like and you're doing like a $1 transaction, maybe you just want to pay your friend back in Bitcoin. Well, that's like already just 10% of your transaction, which is super uneconomical, right? And this makes micropayments impossible, and which is interesting because micropayments open the doors to like many different types of really interesting and unique use cases for Bitcoin. But yeah, these are all things you already know, and we'll go into how Lightning Network kind of fixes these or allows for improvements. So here's an idea. It's a crazy idea. This is super revolutionary, but why not just not put every transaction on the blockchain? And now you might be wondering, like, okay, if we don't put every transaction on the blockchain, then like, what's the point of even using the blockchain, right? Like, we're just not going to take advantage of any of the guarantees of the security, privacy, anonymity, all those guarantees. Well, not quite. And so this is where we introduce the idea of payment channels, right? And so a payment channel is just, and here we say Alice and Bob, but I'll just use, myself and Niche, just it's more fun. Say me and Niche open up a payment channel, between ourselves, right? And so instead of consulting the blockchain every single time, I pay him in Bitcoin, he pays me in Bitcoin, we kind of just like keep a log on ourselves, right? So say we're roommates and I paid for groceries 1 week and he paid for groceries the next week, and we want to like settle at the end of the month. Then what we would do is, instead of consulting the blockchain, we have this payment channel open between us. We would just kind of say like, okay, I have plus 10 Bitcoin, and his groceries cost like 8 Bitcoin. So then for me to settle, he would need to pay it's like 5 Bitcoin to me, 5 Bitcoin to him, and then his 8 Bitcoin becomes 4 Bitcoin to me, 4 Bitcoin to him. And then we just kind of plus minus from our balance sheets. Okay, at the end of the month, we need a result, and I need to have my 9 Bitcoin paid, and he needs to have his 9 Bitcoin paid, and that would be it, right? We wouldn't have to consult the blockchain for 4 different transactions. We would just consult the blockchain for the first transaction, which opens up the payment channel, right? Say the payment channel is depositing my 10 Bitcoin, his 8 Bitcoin.
Mhm.
And then the final transaction, which settles, right? After we've calculated everything, we've calculated the net change in both of our balances, the final transaction would be like, okay, pay out this much to Seon and this much to Nish. That's the idea of a payment channel. And an analogy that I like to use is that of a casino, right? When you enter a casino and you meet the man at the front and you give him your USD in exchange for chips, you can think of that as opening a payment channel, right? You're opening a payment channel between you and the casino. So then you enter the casino with your handful of chips, and you go to all the games. You play some blackjack, play some poker, play some roulette, or maybe play some of the slot machine. And all throughout your day when you're playing in the casino, you're not dealing with USD. You're dealing in chips. You're asking, I'll ask Nish, can I get 5 ones for this 5 if I need ones, or I just lost the dealer, so I need to give him a couple of chips. Like, we're not dealing in USD, we're just dealing in chips, which makes it very simple because you can think of that as just on our private balance sheet, we're just plussing Bitcoin and minusing Bitcoin, right? We don't need to consult the blockchain. We don't need to deal in USD every time we make a transaction. And then at the end of the day, when we're done playing games and we're either up a bunch or down a bunch, second one's much more likely.
Honestly.
Then we'll go back to the guy at the front of the door. We'll be like, okay, here's our chips. Please give me back the USD. You can think of that as the final transaction in a payment channel that settles, right? And so after you're done gaining all your money or losing all your money, then you change it back to USD, and you walk out of the casino with a net positive or a net negative. And you can think of payment channels in the same way. This isn't really a new idea. Payment channels have existed, but what Lightning Network does is it kind of creates a network of payment channels. So let me go to this visual graphic. This is just kind of explaining payment channels. This is all very interesting. And so you get to this graphic of the Lightning Network, right? What payment channels allow is we decrease the number of transactions. Say me and Nish have like 100 transactions because we're like doing something with Bitcoin transactions.
For hot stuff.
Yeah, something with something that requires 100 transactions. What Lightning Network and what payment channels would allow us to do is only have 2 on-chain transactions and then 98 intermediary transactions that aren't on-chain, right? We only have 2 on-chain transactions and an arbitrary, even infinite amount of transactions in between those 2 transactions. And what are those 2 transactions? Well, it's the opening transaction and the closing transaction. In terms of the analogy, it's when you enter the casino and you exchange USD for chips, and then it's when you leave the casino and exchange chips for USD. And so that's the huge thing with Lightning Network is not only are you able to open up a payment channel with one person, but the Lightning Network connects all of its users that are part of the Lightning Network with payment channels with each other. So you can imagine, like, we have Alice here, we got Bob, Dylan, Ethan, Frank, and Chris, right? Alice and Bob have a payment channel. Alice and Dylan have a payment channel. Imagine nodes as users and edges as payment channels. These guys have a payment channel. But what if Alice wants to pay Chris for something, right? Maybe Alice wants to go to Chris's shop and buy, like, I don't know, some used shoes. Well, it would be kind of annoying if you enter a store and you're like, hey, I want to buy this thing, and then you're like, okay, let's have a payment channel with a cashier, and then so you send that, or maybe with the store, and then you send them Bitcoin, and then you wait for the Bitcoin to come, like, you change, come back, or whatever. It's much easier. This is what Lightning Network does. It's much easier to just use the payment channels that already exist, right? Alice has a payment channel with Bob. Bob has a payment channel with Ethan, and Ethan has a payment channel with Chris. And so why not just Alice can send some money to Bob, then Bob sends that same amount of money to Ethan, then Ethan sends that to Chris, and then there we go. At the end of the day, Chris has received the money that Alice was supposed to send Chris, and then Chris gives Alice the used shoes, and then everyone's happy, right? This is what Lightning Network allows for to happen, right? As long as there's a path in between 2 nodes, then a transfer of money can exist that doesn't have to be on chain. This can be off chain, which means that you don't need to pay transaction fees. You don't need to wait for the 6-block confirmation time. You don't need to do all of these things that are required when you are on chain. you just need to use a Lightning Network and, make sure you have that opening transaction that is on chain, keep in mind, to open up the payment channel, and then the closing transaction to settle all balances to, whoever you paid throughout the duration of your stay in the Lightning Network. So again, we'll go into pros and cons to evaluate the Lightning Network. Honestly, my little spiel about the Lightning Network does not do it justice. There's so much greater YouTube videos, so much greater, articles about Lightning Network that will really help you to understand it. I highly encourage you to look into them. But really quickly, assuming that, inside of the network, keep in mind now, I'm not talking about the Bitcoin network, but I'm talking about the Lightning Network, which is, remember, an L2 solution. So it's built on top of the Bitcoin blockchain. Assuming that, there's enough money going around and everyone can spend money and send money to other users, then people can make payments basically instantly. Because keep in mind, all we're doing is exchanging chips, or we're just plussing to a balance sheet and minusing from another balance sheet, right? These are, basically instant when compared to the 6-block confirmation time that is corresponds with on-chain transactions. As I mentioned, you don't need to wait for confirmation times. You only use the actual Bitcoin blockchain. You only use that base layer to settle disputes and close out payment channels, which is super efficient. Now you have, like I mentioned, 2 on-chain transactions, and in between those transactions, infinitely many, arbitrary amount of transactions. And so now 3 transactions per second becomes, who knows how many transactions per second, a huge number that's comparable to Visa, PayPal, MasterCard, whoever, right? Which is why I'm so excited about Lightning Network, because this could truly be the thing that makes Bitcoin, usable on a daily basis, which is kind of, if you ask certain people, the goal of Bitcoin. There are some cons with Lightning Network that can happen, and we can kind of speak about the scalability triangle as well. Number one, these nodes or these users that are part of the network, if we go back here, Alice, Bob, Ethan, Chris, Frank, Dylan, they all have to keep, a decent amount of money locked up in the Lightning Network, right? So when you have Bitcoin locked up in the Lightning Network, then you can't use it elsewhere, because the Lightning Network needs to use it as liquidity to send money to different users of the network. Well, people can, an argument can be made that all that money that's just sitting there in the Lightning Network, locked up in these users' accounts, it's kind of a waste of money. I'm sure many of you have heard about DeFi and all these, yield farming strategies and all these ways that you can, lend cryptocurrencies to other people and make money just by doing that. If you think about it in terms of that, then there's a much more opportunity cost in, staking your coins and putting your coins into DeFi protocols. But there's benefits to Lightning Network and why you would do that. But an argument can be made that this is pretty detrimental to the system. In addition to that, there is a risk of centralization, right? So with this scalability increase, there is a pretty big or a pretty significant centralization risk of, imagine that one node, say if we go back to this picture, imagine Ethan, right? Imagine Ethan's a rich dude, right? He has, all the Bitcoin, he's a Bitcoin whale. He can actually afford to keep his payment channels open way longer than, anyone who has, a small amount of Bitcoin. He can afford to accept payments and route payments to where they're supposed to go much longer than anyone else. And so what this kind of lead to is this hub and spoke topology, where you can imagine this node in the center is Ethan, and everyone else in the network is kind of connected to Ethan in some way or another. And you can imagine this can open up an attack vector in the sense that what if an attacker builds up all these connections with other nodes, but then all of a sudden overnight just takes away all the liquidity. Then there would be a cut in the graph, and then the network wouldn't be as connected as it used to, which could lead to latency issues or payment errors and stuff like that. And so centralization in this case is a very big risk, but there are ways that network is working towards to prevent this type of centralization.
Absolutely.
Any questions?
Let's hear them.
That was Lightning Network.
Shoot. Okay. Yeah. I'll be zooming through the last few sections.
I have 25 minutes left.
Oh yeah, we're chilling.
All right, cool. I mean, if there's no more questions, you can feel free to move forwards.
Let's do it.
Let's get it.
All right, I'm gonna close this lecture off with talking about L2 scaling solutions in the smart contract sort of environment. So when it comes to something like the Lightning Network, it's really awesome, but it's particularly for things where you're working with a single cryptocurrency and you're working with payments specifically. But when you go to something like Ethereum, which you've learned about before, things like Ethereum are just on a different level than something like that, because with Ethereum, you're now working with an execution context. You now can execute any form of code on a blockchain. That's pretty crazy and very crazy. And now with these smart contract execution environments, you can't just create a channel between two people or just two other endpoints on the network. You now need to bring an entire smart contract or this executable context onto the layer 2. So how do you do that? And a popular, modern, and already implemented solution to do that are rollups. And I'll highlight in particular a version of rollups called optimistic rollups. So the way that rollups work, I like to use this metaphor of, if you see in the top right, the Flying Dutchman ship from SpongeBob. You kind of see it as this like floating thing above the entire sea, and okay, what happens on the ship stays on the ship, and okay, you can climb up this anchor to go up to the ship, and okay, jump down. And what a rollup essentially is a contract on the blockchain. Let's start with Ethereum and just stay on Ethereum. A contract on Ethereum that is anchored directly to the Ethereum blockchain. So similar to the Lightning Network with that casino metaphor, you're entering and exiting a rollup with transactions on Ethereum. And then whatever happens in the middle, in this time it's smart contract functions being called. This is now happening within the rollups context. So you're starting and you're entering a rollup, doing stuff on the rollup, and you're making changes to state that will then be saved in the end once you get back onto Ethereum. How do we make sure that these changes to state are legal, proper, and approved? And the way that we do that, and the way that we basically manage security in general with rollups, are these proofs. So with optimistic rollups, we use things called fraud proofs. And the way fraud proofs work are, when you exit the rollup itself, there is a 1 to 2 week period in which anyone can challenge the rollup itself and be like, hey, I think you're wrong. I think the state that you ended up with, I don't want that. Or, oh, that's wrong. It shouldn't be like that. And then it's up to the rollup contract itself to come out with this proof and be like, no, I was told to do X. And okay, I have this proof that I executed exactly that. And then you will verify that proof. And then through that, you'll be verifying the correctness of this off-chain computation. So that's the way that these rollups work in general. Then once the proof deadline has been crossed, then everything is back to being finalized on Ethereum. So the entire timeline is sort of create a rollup, create a relationship with your rollup contract, execute a bunch, work with it as much as you want in a very cheap way, because now you're no longer making transactions on Ethereum, and then exiting and then using this time period to submit proofs and verify state. What is awesome about rollups is that they're out and implemented right now. For things like optimistic rollups, there are a few implementations out there in the world. Two names are Optimism and Arbitum. If you're following DeFi at all, you'll likely have known that the latest Uniswap version will also be deployed on Optimism. So now you can swap tokens for a fraction of a cent rather than the $100 you would have to pay right now. It's just too much. And so those are optimistic rollups. There's also a second form of rollups called zero knowledge rollups. And these use, rather than fraud proofs to validate rollup state, zero knowledge proofs. These really often computationally expensive, so that's why they're not out yet, but extremely fast and extremely fast in terms of finality rollups, which means when I mention finality, I mean for ZK rollups, you no longer have this 1 week period of challenge, which is much, much better when you think about it. You enter the rollup, and when you exit, you know that you're fully back on Ethereum. So ZK rollups in the long term are definitely the move, but for right now, the optimistic rollups are the ones that have been able to be deployed. And so these rollups offer a fair deal of scalability, often 300 to 400 times in terms of gas costs, which is pretty awesome. So you're able to handle much more transactions and a transactions load on the layer 2. But of course, on the other side of the scalability triangle, you have to worry quite a bit about security, and that's why you might have to make trade-offs in terms of like, okay, this 1 to 2 week challenge period to get back to finality on Ethereum. Decentralization is again a little orthogonal. Nothing too much is happening there, because as long as you once again are implementing this right, the decentralized level, the level of decentralization is something like Ethereum won't be harmed at all.
Yeah.
So those are rollups. Probably one of the most complicated things out there right now in distributed systems and blockchain. But I hope the concept is kind of meshing nicely in y'all's heads. So I'll pause for questions on rollups.
Well, can I just say, that's a great analogy with the Flying Dutchman. Just
I know,
anchor
right?
down and they come up. That made it click for me. That was good.
Good stuff. Good stuff.
Good stuff. Good stuff.
Love me some metaphors.
Yes, sir.
All right.
Do you have any details on how fraud proofs, or like the general, like what a fraud proof kind of looks like?
So I think oftentimes
Like, what are you proving first of all?
Yeah, it's a piece of state, and basically like how you got to that piece of state. So like, okay, this state change, like, oh, okay, now this guy's token balances are X and Y.
Remember, Ethereum virtual machine is basically just state machine. It's just
exactly
changing every
exactly. So then the proof is kind of like, here I have this. Oftentimes it's a Merkle proof about, okay, I can show you that this state is actually as it was. Caused by this operation that I was instructed to do. So yeah, you're basically able to prove that, like, okay, I was asked to make this make this function call, and then okay, it caused this.
Gotcha.
Vitalik's post is really useful for thinking about that.
Right.
So yeah, I'll drop that as well. But yeah, any other questions on rollups? All right. I'll just end us off with a little bit of inspiration. Scalability is the most modern problem, the most modern concept in blockchain. So it's really great that you're learning it right now. I mean, advancements in scalability are happening as we speak. I have mentioned ETH 2.0 a little bit. That is basically Ethereum's entire movement to scale itself. It's moving to a sharded blockchain, like I mentioned, where phase 0, basically let's slowly transition into this blockchain, has just completed in December. They had to lock up a bunch of Ether in these migration contracts, and everyone in the Ethereum community kind of came together and dropped their ETH in there to become validators. ETH 2.0 also moves them towards a proof of stake blockchain, a little less on scalability, but just a cool topic. There are decentralized apps on all sorts of blockchains, not just Ethereum, building out L2 versions of their apps. So just a few names here, Aave is moving and they're working on a side chain. Synthetics is on an L2. I think they're on Optimism itself. And of course, there's Ethereum 2.0. And of course, I've mentioned Uniswap as well. So these advances in scalability are things you can try out right now. And I think that's the most important part of the scalability lecture and the motivation for scalability here. Blockchains right now aren't accessible to all, which just feels so weird. It's the greatest criticism of them right now. You kind of see it everywhere, even with things like this boom of NFTs. NFTs are they're only able to be collectibles right now because you can only like afford to just buy an NFT once on like Ethereum. But things like scalability will allow you to do much more on a blockchain and just have much more powerful blockchains for all, which is honestly just amazing. So it's a great time to kind of follow scalability. If you're interested in this at all, especially as a developer, you can hit us up to try and see how you can kind of offer your skills and dive in and learn a bunch and develop on your own. Even if you're not a technical person, just to be familiar with all this is really awesome. It's a fun space to be in. So we're here for that. But yeah, that's what we're here.
Yeah,
Any
and
issues?
I believe that pretty much concludes this lecture.
Yeah.
Thank you so much for coming. Thank you so much for spending your Thursday evening with us. We had a great time. Hopefully you guys learned a little bit, and hopefully you guys take away. Remember that mental model of the scalability triangle. That's how you evaluate scalability solutions in the future, and it's how you yourself can kind of form your own opinions on scalability solutions, because that's very important, especially in this decentralized and this this ecosystem that focuses on individualism and decentralization. So yeah, thank you so much for coming. We'll stick around for a couple of extra questions. There will be a quiz, so review the slides. Slides will be up on B courses as per usual. Recording will also be on B courses. We recorded this, right? Oh, thank God. Okay.
Yeah.
And thank you for coming to lecture 8, and we'll see you in lecture 9.
All right. Thank you all
Have a
so
good one.
much. Thank you.
Thank you for your great questions, Ryder. Really, really appreciate it.
What's up, Brian? What do you think about the lecture?
Yeah, any feedback, bro?
Bro, you guys are so good at explaining.
Thank you, man. Thank you. I should be good. I did the same exact lecture last semester, so second time around, if I'm not good, then I'm not doing something right. But Nisha, the real OG. He's been on this for forever.
Soon had me grind this, but no, yeah, Brian. Soon next semester, I want to see you lecturing.
Got to see you lecturing too,
The
man.
entire audience.
You're a freshman, right, Brian?
I'm a sophomore.
Sophomore. Okay.
Bro, they could fully happen, man.
Yeah, dude, just hop in. I mean,
there's a lecture you really want to lecture on.
And we want everyone lecturing that.
Let's do it.
It's a great experience. Great way to learn. Honestly, like I learned so much just by like preparing slides
Straight
and
up.
lecturing. So
You feel like an expert.
yeah.
Yeah, how do you guys learn all the material for the lectures?
So this is kind of interesting. Last semester, me and if you know Alpin, he's also in BAB. We spent a lot of time almost revamping this entire lecture, just because it had been really outdated. And so for me, where I kind of got my information from was I attended this university study group, and Nish was also in it, and a bunch of other BAB members last semester. That was directed and conducted by Chaincode, which is how would you describe it? Like a research group that contributes to Bitcoin Core. It's a bunch of Bitcoin core devs. Bitcoin community core devs. The devs get paid, and it's like this company basically. And they started this university initiative, and they had a bunch of university students from blockchain clubs all across America. So there's people from Berkeley, obviously, also Michigan, Carnegie Mellon, Stanford. No. It's just all around, right?
All over.
And so they just walked us through, I think it was 5 or 6 weeks of just Bitcoin content every week. They gave us a bunch of readings. One of the weeks was SegWit. We had a whole week dedicated solely to SegWit. We had a whole week dedicated to scalability. So Taproot was in there. And that's where I learned a lot of my stuff. It was straight from Bitcoin core devs. Gloria was also there, the previous co-president of BAB. Yeah. And so it was a really cool experience. And that's where I got a lot of my information from. And that's where I just kind of transferred that into here. But honestly, in general, it's just like stuff we learn in BAB, the fundamentals content. I took this fundamentals lecture, in my freshman year, and I learned a lot from there. And also, I've learned so much from Nish. Nish holds a bunch of discussions, almost on a weekly basis, just about random stuff in the blockchain space that I always like to hop in and learn from him. So it's just been, inside the club, there's so many opportunities to learn. It's just all about saying yes and just trying new things,
Yeah, I like that last part. Yeah, a lot of times there's just like huge just pools of resources of information. So yeah, first we have just what BAB gives you, and then also honestly just all the time there are these other huge chasms of resources. So first there's the Chaincode Bitcoin group. I learned a lot about like Ethereum scalability, things like rollups, just by reading online. Like there's a really awesome article by Vitalik on just a guide to rollups, and really smart people just create these amazing Medium posts online, just explaining these extremely complicated topics. Yeah. Even just on Twitter, people will put down thought pieces and you'll slowly catch on a little thing. So it's kind of like this,
Twitter is huge.
Yeah. It's just this gradual like learning experience through stuff like Twitter, BAB. I learned about rollups first because it was like mentioned in a project I was doing like a year ago, because we were like looking at how to scale like blockchains in a practical use case, and someone mentioned rollups. So I kind of learned it there. It's kind of crazy that was a year ago.
Yeah, learning by doing, man.
yeah, just like diving in and like joining a bunch of stuff, you'll just immerse yourself, because a lot of times it might seem like there's so much or like way too much to even learn, but honestly it becomes very
everyone feels that. Niche feels that way.
Yeah,
he's
bro.
Yeah, he's learned so much. Right, I'm curious, are there any topics that you're specifically interested in, or like any topics that you'd be down to like kind of deep dive in, and maybe we can like connect you to people who are doing deep dives or maybe even projects and stuff?
An Ethereum deep dive would be pretty cool.
Ethereum, okay. Yeah,
Ooh,
I mean, we have a dev decal. I think that's the first thing that came to mind. We have a dev decal where they, you know, I think they do a deep dive in Ethereum. I think it's a little bit more focused on the actual Solidity code and the technical part, but you know, again, learning by doing.
Brian, were you there for the Ethereum attacks white paper circle?
I think I missed that one.
Yeah, I think you would have really liked that one. Yeah. Sadly, I haven't been recording them, but that one, I'll DM you the paper. That one's a really fun one to like understand Ethereum better. The Ethereum white paper is all over the place, and like Ethereum is in such a different state. So don't worry about that. But yeah, there's some nice like Ethereum explained things. It's really important. I'm glad you're interested in just like getting that down.
Yeah.
So I'll DM you a bunch of things just about Ethereum. And like you'll slowly catch up on things, even if you just on Twitter follow like just Ethereum core devs. I can like give you some names as well. And they talk about the current state of Ethereum in many ways. So they talk about EIP 1559, which was the most previous white paper circle as well. So I hope they recorded that. That's like the fee burn Ethereum thing.
Okay.
Yeah. So that one's really cool. That's a very current events Ethereum thing. There are a few other Ethereum themed white papers we'll talk and read about. So those will be good. But yeah, just a bunch of reading. There's all you really got to do. Reading, fun conferences. Yeah, miss conferences.
Yeah, but don't forget your roots, man. Bitcoin is still king.
Never forget.
Bitcoin is still very important.
Bitcoin,
very relevant.
you can learn how to reason yourself around any blockchain by just like diving into Bitcoin.
Exactly. And if you want Bitcoin, more Bitcoin knowledge, Sashir is definitely the person to go to. He actually contributes to Bitcoin Core.
Most definitely.
So yeah.
Yeah, you should talk to him about joining his little Bitcoin working group as well. You can contribute to Bitcoin yourself, bro.
Yep.
It'd be fun.
That's so cool. Yeah. Do the Bitcoin devs, like core devs, is it like purely out of like passion that they do it, or is there like incentive?
Yeah, a lot of times now people are building grant programs a lot of times for developers. So now like Gloria is getting a grant. She's also getting a grant from like Brink, this other Bitcoin community like company type thing. So now you're getting community funding for developers, which is really cool because developers are the most important parts of any blockchain ecosystem. So opting get paid there.
But honestly, I would say like these Bitcoin core devs, if they were to work, somewhere else, Fang or some other security company or something, they would be making so much more than they are working on Bitcoin core, right? I honestly do think that it's almost purely out of passion that they kind of dedicate their time.
Yeah, that makes a lot of sense.
Because Bitcoin core devs, they basically are full time on Bitcoin. They're constantly updating, constantly coding, constantly looking for bugs, security threats and risks. And so, it's just really cool to see people following their passions, because Bitcoin Core obviously is very close to certain people's hearts. Yeah,
they're doing something that they like genuinely love, and then you like honestly for Gloria, she literally had a Fang offer, but she didn't even know how she was gonna live being a full-time Bitcoin Core developer, but she just sent it because she knew it was something that she was in love with, which is pretty admirable. And then
that is awesome.
The money found its way wherever to make sure that she's all right. Oftentimes there are like just companies that will pay you to do Bitcoin Core work as well. Like Chaincode was one of them, and like Bolt Labs and like all these different things. So like it becomes easier than you think, which is pretty crazy.
Especially like as time progresses, like in this day and age when Bitcoin is breaking through all-time highs like they're nothing.
It's true. There's stability in like the chaos. Of everything.
That's a good way to put it, honestly.
Yeah, it's pretty cool. Yeah. But
Yeah.
you guys are awesome. Thank you so much.
Thank you,
No,
bro.
thank you so much for stopping by.
You're
and-
awesome,
and
bro.
You're awesome too, man.
Yeah, I hope everything has been going good for you.
Yeah, it's only the beginning, man. Only the beginning.
Only the beginning.
We're gonna hop off now. We do got. Oh, that was almost full 2 hours. We really killed that.
we fucking
That
spent
was
that
fun.
time.
That was fun. Oh, we're still recording. Interesting. Okay.
Oh.
Let's